In this video, we are going to talk about units, precision, and accuracy. Now, there are many systems of units that we can use, imperial, metric, and so forth. The unit system that we use most often in physics is known as the SI or the MKS system. MKS stands for meters, kilograms, and seconds. The base units in the SI or MKS system include the second, the meter, and the kilogram. Now, a second is defined based on what is known as a hyperfine transition in cesium. So it turns out that the ground state of cesium, if you hit it with radiation at just the right frequency, it will interact with the radiation and will scatter the microwaves. And so people figured out they could make very precise clocks using cesium and decided, why don't we just define the second in terms of the microwave frequency that the cesium will scatter. And so now the second is defined to be 9,192,631,770 oscillations of this resonance in cesium. So this is what we call an atomic standard. If all of the clocks in the world were destroyed, you could come back and make a new clock that would still fit this standard definition. This is opposed to what we used to have, which were things called artifact standards, where there was something that we measured, and if something happened to that thing, it would change our measurement system. The meter is actually defined in terms of the speed of light. So the way that we define the meter today is we say the speed of light, which we often call c, we define it to be precisely 299,792,458 meters per second. And then we can figure out what a meter is just by measuring how far light travels in 1 over that number of seconds. The kilogram, until just last year, was actually defined with an artifact standard. It turns out that mass was a difficult thing to make an atomic standard for. But last year they adopted a new, so before last year there was like a chunk of metal that sat in a vault in Paris, and that was the kilogram, and everything was compared to that. Not an ideal standard because, if something happens to it, now we don't know what a kilogram really is. And in fact, something always happens to it. The metal oxidizes, different things happen. But now there is an atomic definition of mass based on a Kibble balance, which basically balances gravity with electromagnetic forces acting on an object, which can be calculated precisely. And then local gravity can be measured precisely as well. There are some other base units in the MKS system. The unit of current is the ampere. The unit of temperature is Kelvin. The unit of large number of things is called the mole, and we'll talk about that later in the semester. And the standard for luminous intensity is the candela. In addition to these base units, there are also derived units. For example, the SI unit of velocity is meters per second. We don't need a new unit because it's already defined. We've already defined meters and seconds. The SI unit for volume is meters cubed. Some of these derived units have actual names of their own. For example, the SI unit of force is known as the Newton, but it's not a base unit, it's a derived unit, because 1 Newton is equal to 1 kilogram meters per second squared. The unit of energy is the joule, but again, this is a derived unit because 1 joule is 1 kilogram per meter squared, or 1 kilogram times meter squared per second squared. And the SI unit of pressure is the Pascal, which is a Newton per meter squared, which is the same thing as kilograms per meter second squared. And the SI unit of power are known as watts. 1 watt is 1 joule per second, but joule's not a base unit either, so we can write power in terms of base units as kilograms meters squared per second cubed. Now, how do we use units in physics? Well, when we work a problem, our variables, the quantities we put into our variables have units. So for example, imagine I measure the average velocity of some object over some time delta t. So I can find the velocity by taking how far the thing moved, delta x, and divide that by the time, delta t. And let's say that delta x is 10 miles and delta t is 3.5 hours. We just put those units in our equation, and then I take 10 divided by 3.5 and I get 2.86, and then the miles and the hours, they stay there. So it's 2.86 miles per hour. If I want to find the volume of a prismatic shape, I just take the length times the width times the height. But length, width, and height have units. So imagine that the length is 10 centimeters, the width is 3 centimeters, and the height is 2 centimeters. I just put those units in there, all right? And then 10 times 3 times 2 is 60, and centimeters times centimeters times centimeters is centimeters cubed. And so now I have my volume, and it is in units of centimeters cubed. Now, checking units is a really good thing to do. Once you work a problem, you should make sure that what you get has the units that you should have gotten. So for this problem, let's assume that t is time, has units of seconds, v is velocity, has units of meters per second, a, acceleration, has units of meters per second squared, and f, frequency, has units of 1 over seconds. So imagine I worked a problem and I found this was my solution. Velocity is acceleration divided by frequency plus time. Well, I go and I plug my units in. Velocity should have units of meters per second. So the stuff on the left needs to be meters per second, which means the stuff on the right should be meters per second. Well, acceleration has units of meters per second squared, so I put that in there. Frequency has units of 1 over seconds. Time has units of seconds. And I look at this and I'm like, oh no, I can't do this. I can't add 1 over seconds to seconds. That's like adding apples and oranges to try and find how many potatoes you have. All right? I cannot add things together with different units. So I know there's a problem with this equation. And if I'd come up with that equation while working a physics problem, I would say to myself, oh, the units don't work out. I must have made a mistake. I better go back and redo this problem. Let's look at this one. Velocity is acceleration over frequency. So imagine I get this solution to one of my problems, and I look at the units. The left side should be meters per second. Well, the right side, acceleration is meters per second squared, and frequency is 1 over seconds. But this seconds down there cancels with one of the seconds up here, and I'm left with meters per second equals meters per second. And so it looks like the units work. That doesn't guarantee that I did the problem right, but the units work, and so that's encouraging. Maybe I did it right. Let's look at this here. Imagine I did a physics problem and I came up with this answer for velocity. Well, if we look at this, velocity has units of meters per second. Well, frequency has units of 1 over seconds, time has units of seconds, and frequency again has units of 1 over seconds. Well, 1 over seconds is just seconds, so I can add these two together just fine. Everything inside this parentheses will have units of seconds. But if I take that and then I multiply by 1 over seconds, I end up with something which has no units, unitless. But my velocity was supposed to have units of meters per second, so my answer does not have the units that my answer needs to have. So I know there's a problem with that equation. I must have made a mistake somewhere working out the problem. Now we're going to talk about converting units. For example, what if I wanted to convert 11.2 feet into meters? Well, I just go on Google and say, convert 11.2 feet to meters, and it tells me, right? But sometimes Google won't do that for you. You may have to do this. You may have to do some units conversions on your own. So this is how you do it. Well, first, I need to know something about different length units. So imagine that you know that 1 foot is 12 inches. Most people know that. All right, and I can look up, or if you may want to remember, 1 inch is 2.54 centimeters. Okay, but that's still not meters, but I can find a relationship between centimeters and meters because I know 100 centimeters is 1 meter. So what I'm going to do is I'm going to start with 11.2 feet, and I'm going to multiply it by 1, because if I multiply it by 1, it won't change, right? but I'm going to write 1 in a funny way. I'm going to write 1 as 12 inches over 1 foot. 12 inches equals 1 foot, so 12 inches over 1 foot is just 1. So if I multiply 11.2 feet by 12 inches over 1 foot, I still have the same quantity. I'm just multiplying by 1. But now notice those units cancel. Feet over feet is 1. Okay? So now I have inches. I need to convert from inches to centimeters. So I'll just multiply by 1. I'll multiply by 2.54 centimeters over 1 inch. And because 2.54 centimeters is equal to 1 inch, this ratio is just 1. And now the inches cancel out. Now I have it in centimeters. Now I just need to convert to meters by multiplying by 1 meter over 100 centimeters. This is just 1 because 1 meter is equal to 100 centimeters. So it's something divided by the same thing. That's 1. Now my centimeters cancel, and so I'm left with just 11.2 feet equals 11.2 times 12 times 2.54 divided by 100 meters, or 3.41376 meters. So that's how you convert units. You just multiply by 1. Now, there's some common metric prefixes that we use. The ones in gray are the ones we really won't be using in this course, but they'll show up in other places, so they're worth knowing. But basically, for example, kilo is represented with a small k, and that's 10 to the third. So 1 kilogram is 10 to the third, or 1,000 grams. Mega is 10 to the sixth. So 1 megameter would be 1,000,000 meters, or 10 to the sixth meters. Over here, micro is 10 to the minus 6, 1 millionth. So 1 micrometer is 1 millionth of a meter, also known as a micron. All right? A nanometer is 10 to the minus 9 meters. All right? Notice most of these prefixes that we use, it's a factor of 10 to a power of 3. 3, 6, 9, 12, 15. 3, 6, 9, 12, 15. The one exception is centimeter, or centa, that gets often used when we use a length, centimeters. But mostly the ones we deal with have a power of or a factor of 3 up here in the top. Okay? All right. Now, scientific notation. In scientific notation, what we do is we write a number as something point something 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 times 10 to the something. All right? And it allows us to write things that are very big or things that are very small without having to write a whole lot of zeros. For example, 1,538.5, I can just write that as 1.5385 times 10 to the third. All right? So 10 to the third is 1,000. Multiplying by 1,000 moves the decimal 1, 2, 3 points, and so I see this indeed is equal to this. That's not any more compact. Why would I bother doing that? Well, for this number, maybe it's not that useful. But what about this number here? What if I have 9,700,000,000, and I want to write that down? That's a lot of zeros to keep track of, but we can just write it this way. We can say, look, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to move the decimal 9 places to the left, and then multiply by 10 to the 9th, because that will move it 9 places back to the right. And so the number on the left then is equal to the number on the right. So the number on the right is the same as the one on the left, written in scientific notation. And I don't have to deal with all of those zeros. So I can write very big numbers compactly using scientific notation. The diameter of the Earth is 12,742,000 meters, right? I can write that as 1.2742 times 10 to the 7th meters. So this is the same quantity, but in scientific notation. Scientific notation is also nice when you multiply things together, right? Because you don't have to worry about all those zeros. If I multiplied this times this, I just multiply the negative 9.7 times the 1.2742, and then it's going to be 10 to the, what happens when I multiply 10 to the 9th times 10 to the 7th? I just add the exponents, and that's going to be 10 to the 16. I can also write very small numbers. For example, 12 nanometers is remember we said nanos 10 to the minus 9, right? So 10 nanometers, there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We have to move the decimal place 9 places. So 12 nanometers is written like this with a lot of zeros, but that is the same as, what in the world? Okay, I apparently copied and pasted something, and I got something which is not quite right. So let's cross that out. I don't know where that came from. It's really equal to 1.2 times 10 to the, remember nanos point is 10 to the minus 9, but I have 12 nanometers, not 1.2 nanometers. So this is going to be 10 to the 10th. So there we go. All right, 5 picofarads. That's lots of zeros if I write it out traditionally, but I can also write that as 5 times 10 to the minus 12 farads. So you can write very small things in scientific notation. All right, now we're going to talk about the difference between precision and accuracy. So imagine you're shooting at a target and your bullet holes land in these locations. All right, that is very precise shooting. Precise meaning repeatable. I'm always hitting the same place. If I have an instrument that measures something with high precision, that means if I measure the same quantity, I will get the same result over and over again. I can get many digits of precision. Now, I might not necessarily measure the right value, just like our target. We're not hitting the bullseye, but we're always hitting about the same place every time. So you don't necessarily get the right value. If I have a machine with an instrument that measures with high precision, I don't necessarily get the right value, but I get the same number every time, and I can calibrate. If I have something that's known that I can calibrate to, I can calibrate this to get accuracy. What is accuracy? Accuracy means hitting the center, the bullseye, measuring the actually right number. Now, I may have a device which measures with low accuracy. That's like shooting and having a big spread, but on average, my bullets are on the center. So the average of many measurements give the correct value. That's what accuracy would mean. Now, if I have precision and accuracy, I hit close to the bullseye every time. So that would be an instrument where my measurements that I make are all very close together. I repeatedly get the same measurement, and it's close to the right measurement. So here's another example. Imagine that you were playing a frequency. There was some sound that was being played, and you wanted to measure what the frequency is. And let's say that the correct frequency is 500 hertz. And so I measure this on a spectrum analyzer. And imagine that my spectrum analyzer will give you kind of like how much sound there is as a function of frequency. And imagine my spectrum analyzer gives me this. My spectrum analyzer has two problems. It's got noise. See all the noise? Also, its response isn't infinitely sharp. So if I go and try and determine what the frequency is, I kind of have to look at this curve and figure out where the middle of it is. And if I do that very carefully, I can get a nice accurate measurement. But because of the noise and such a broad spread, I might not get the right answer. A spectrum analyzer with high precision might look like this, where I have less noise and my peak is sharper, so I can more precisely determine the value of the frequency. Unfortunately, this spectrum analyzer gives me the wrong frequency, but it does it precisely. I can repeatedly get the same measurement. And if I'm careful, I can calibrate the instrument then and get something which is both precise and accurate, which would be this green curve right here. Now, significant figures, or sig figs. When we write down a quantity, right? If I make a measurement and I write down this thing is 11.4 meters long, right? It's not really 11.4 meters. There's always error in my measurements. And so there are some conventions we use to try and indicate how much we trust this measurement, to what degree we trust this measurement. And one way is with significant figures. So if I write down 1.007, if I measure something and it comes out to be 1.007, how many significant figures are there? That is 4 significant figures. I have 4 digits that tell me something meaningful about this measurement. This number right here, 0.00235, That's 3 significant digits. The leading zeros don't tell me anything, right? If I were off, if I have an object which is 0.00235 meters wide, but my measurement is off by 0.00235, I have no information about the object. These zeros are not significant. They don't add to my significant figures. If I have the quantity 1,424 kilometers, that's 4 significant figures. There's 4 digits of actual useful data. If I tell you that n is equal to 4 and n is an integer, well, since I know that it's an integer, it's exact. It's like I have an infinite number of significant figures. How about 1? If I say this is 1 meter long, how many significant figures do I have? Well, is it exactly 1 meter long? Probably not. So when I write down 1 meter, it's kind of like confusing. You know, how accurate, how much do I trust this measurement? How accurate is this measurement? Well, I could instead write it like this, 1.00. So trailing zeros say, hey, this is 0, but I've actually measured that that digit is 0. So if I write down 1.00 meters, that means I have 3 significant figures, that I believe that this measurement is correct to something on the order of a centimeter, right? If I made a measurement that was accurate on the millimeter scale, I would have written 1.000 meters, so that you see there's actually an additional significant figure. What about 100 million seconds? How many significant figures? Are all of those zeros significant, or are they just placeholders, right? I mean, I measure something and it's 100 million seconds. Did I measure it down to the second? Or, I mean, I don't know. How many of those zeros are significant? It's hard to tell when you write it this way. This is one nice thing about scientific notation. I could have written it this way, 1.000 times 10 to the 8 seconds. And you look at that and you say, those 3 zeros didn't need to be there, because the 10 to the 8 takes care of that. So those 3 zeros must have meaning. The person who made this measurement must know that those really are zeros. But after that, we don't know whether it's 0 or what. So 1.000 times 10 to the 8 seconds clearly has 4 significant figures. There's another way we can give uncertainty that is used often, and that is you write your number and then you put in parentheses another number. And what that means is that, so this number in the parentheses, it has 2 digits, and that means that these last 2 digits could vary by plus or minus this amount. So this means this number right here is my best guess as to what the number is, but I only trust it to within 0.00011. That's what that 11 in parentheses means. Now, what do you need to know about significant figures? They're more complicated than you might think. So the book gives some rules of thumb, and we'll go over those in a minute, but oftentimes those rules of thumb aren't good enough. So for now, just note a few things. First of all, rounding error can accumulate. So for example, imagine I give you a bunch of numbers and I say add them together and give me your answer to 3 significant digits. All right, well, if you add them together with all the digits, you get 5.967, and then at the end, you're going to round that to 3 significant digits, and you say, oh, the answer is 5.97. If you round the numbers first and then add them, the round-off error can accumulate, and you end up getting the wrong value to 3 significant digits. All right, so you need to keep these extra digits until you get to the end. One thing that can happen is if you subtract 2 very similar numbers. So here's a number with 5 significant digits, and here's a number with 5 significant digits. But when we subtract them, everything goes to 0 except this last digit. How many significant digits do I have now? I have 1. So I started with 5 in each of those 2 things, but when I subtracted them, I ended up with an answer that only has 1 significant digit. So be careful when you're subtracting similar numbers. So basically the takeaway is when you work homework or exam problems, keep all of the digits in your calculator. If you work part A and you get an answer and I ask for 3 significant digits and you write down 3 significant digits, and then part B has you use the answer from part A to do something else, don't use the one that's rounded to 3 significant digits. Use the one that's in your calculator that has all the digits. Okay, so here's some significant figures rules of thumb that sort of work most of the time. When you multiply or divide, the number of significant digits you end up with in your answer is equal to the number of significant digits of the thing you multiplied, which has the smallest number of significant digits. So if I multiply 1.23 times 0.002435, the first number has 3 significant digits, the second has 4. So after I do the multiplication, I get all these digits, but I know that they don't really count. I have to truncate then down, round to 3 significant digits, which is 0.00300. So my answer will have 3 digits that I can count on. All right, so if I ask you to multiply this and give your answer to 3 significant digits, this is what you give. But if you take this and use it to do something else, you want to use what's in your calculator. You don't want to round until you get to the end, all right? 7.335 divided by 1.2, just like multiplication, we get our answer, but then the number of digits that are significant is equal to the smallest of the two, which would be this 1.2 only has 2 significant digits, so after we get our answer, we round to 2 significant digits. But remember, if this is an intermediate step, we keep all of this stuff until we get to the end. When you add or subtract, basically the number of significant digits depends on, basically you look at the accuracy, that when I add this number here has accuracy to the 10 thousandths, but this number only has accuracy to the 1/10th point. So when I add them together, uncertainty in what comes after this 0.1 means I can't trust the stuff. I mean, I may have accuracy over here, but I have all that uncertainty in this number. So in the end, I have to round to the 10th place. Here I have 2.2 minus 0.001, all right? And this is the number I get, but then I say, well, look, this number has accuracy out to the thousandths, but this only has accuracy out to the 10th. So in my result, I should only trust it out to the 10th place, and so I'm going to round accordingly. Now, exponentials, logarithms, and cosines can do all kinds of funny things and mess with your significant digits. So normally in this class, I will not worry a whole lot about finding how many digits are really significant, and I'll just tell you, give your answer to 3 significant digits, or give your answer to an accuracy of 0.001 meters or something like that. And we're not going to worry a whole lot about significant digits in this class. I just want you to know that they exist. And that is the end of today's discussion.